Okay. So, that's what I'm going to be talking about. And let me first a problem related with the smoothings of singularities. That has to do with the specialization that George mentioned. So, very simple things. Let me start with some history. If we have a two-dimensional surface with a normal isolated singularity, not like V star, the V minus the singular point, so this is a smooth complex manifold. And in 78, Dorothy introduced a concept. He said that the germ was numerically Gorenstein if the canonical bundle of this manifold is trivial as a complex vector bundle, but topologically trivial, not holomorphically, but topologically trivial. Then he called the singularity numerically Gorenstein. And there are many such examples. For example, if you take any line bundle over the Riemann sphere, which are in class less than -2, and you blow it down, you get one such a surface. Okay? That's equivalent to saying that if you take a resolution, say a good resolution, then the canonical class of this guy, which can be defined topologically, say by the adjunction formula, numerically Gorenstein is equivalent to saying that this is an integral class. Okay. And then, I don't know if you need the link, yes, you need the link, then Dorfey proved the following theorem. If you have that the singularity is smoothable, and you assume that the tangent bundle of the Milnor fiber is topologically trivial, then denote the signature of the Milnor fiber in this way. This is the Euler characteristic, which is mu plus 1, where mu is the Milnor number, which is when V is a complete intersection, we know that the Milnor fiber has the homotopy type of a bouquet of spheres of middle dimension, and the Milnor number is the number of spheres. No, forget for the moment about this. This is not in Dorfey's theorem. This only exists when the singularity actually is Gorenstein. Okay, so take the other characteristic of the Milnor fiber. You have the self-intersection of the canonical class of the resolution, and then you prove this signature formula for the Milnor fiber. This is the signature of the Milnor fiber that is given by the Euler characteristic plus invariance of the resolution. And this itself is also determined by invariance of the resolution.
Singularity is isolated.
Isolated, normal in dimension 2. Matthias, you have a question?
Yeah. V tilde is not the Milnor fiber, but the resolution?
V tilde is the resolution and F is the Milnor fiber. Okay? So this is telling you how to relate invariance of the Milnor fiber with invariance, how to determine them from invariance of the resolution. Okay? And he's assuming that the singularity is numerically Gorenstein and smoothable, and the tangent bundle is topologically trivial. You have this formula. Then he conjectured, and I proved it, that if the germ is actually Gorenstein and is smoothable, then the Milnor fiber, its tangent bundle, is automatically trivial. This was a conjecture he stated, and I proved it. Okay? So that means that this theorem applies for all Gorenstein smoothable singularities. Then, and the proof that for Gorenstein singularities, this guy is trivial was by proving that its first Chern class is 0. In that case, that was enough for proving that this guy is trivial. So, several questions related. Well, if you have a germ which is numerically Gorenstein and is smoothable, we know that if it is Gorenstein, this is trivial. If this is only numerically Gorenstein, is this trivial? I don't know. The proof I gave used strongly that it was actually Gorenstein. That there was a lower vanishing holomorphic to form, blah, 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 blah. Okay? So this is something, I don't know. what about higher dimensions? If we have a smoothable singularity in general, what can we say about the chain classes of the tangent bundle of the Milnor fiber? Smooth. Absolutely nothing is known as far as I know. For instance, if this germ is a complete intersection, then this guy is trivial. That's very easy to prove. But if it is not a complete intersection,
By smoothing, close everything to the generation.
it means that you have a one parameter family, so to say, of smooth manifolds, all of them smooth, that degenerate, it's a flat family that degenerates to the variety.
Like a strong feeling that has to do with germ food and flax.
Yeah. Okay. These are local germs. It's a germ. It's a germ.
It's a germ.
Yeah, it's a germ. Yes.
germ.
Yeah.
So you are looking at the global content.
Yes, exactly. Now you were.
Yeah, how important is the Gorenstein assumption? Because if it's not Gorenstein, then I think there are examples where this tangent bundle is not trivial. Is it crucial?
Well, in dimension 2, I know that if it is Gorenstein, then the tangent bundle is trivial.
Yeah, I mean the numerically Gorenstein. Yeah, okay.
No, I mean, if you remove the condition of being numerically Gorenstein, some way it is equivalent to saying that the tangent bundle, that this tangent bundle restricted to the boundary is trivial. So if you know that it is restricted to the boundary, it is trivial. Is it all of it trivial? If you remove the condition that this is trivial on the boundary, then it will not be trivial. No way. Okay? So it is necessary.
Why is it trivial for complete intersections? Just intuitively, why?
No, it's a very simple argument. For a compact manifold with a complex structure, with an almost complex structure, and with non-empty boundary, the tangent bundle is trivial if and only if its stable tangent bundle is trivial. And its stable tangent bundle is the tangent bundle plus the normal bundle.
Ah, okay. I see.
And if there is a complete intersection,
Yes.
okay, so that's why. Okay. No.
But you would also directly get it from the universal recognition space.
Sorry?
It's a germ of a map, and you just take the generic fiber.
Yeah.
So the tangent boundary
You
is
pull it
pulled back from
yeah,
the fiber
yeah.
of a point. So
Yeah.
it's automatically
Mhm.
perfect.
Yes.
Well, so in general, if you have an n-dimensional isolated smoothable singularity, and we can take the Milnor fiber of the smoothing. Just a remark, a singularity can have many different smoothings. So this is not unique. When it's a complete intersection, this guy is essentially unique. In general, there can be many Milnor fibers. But given a Milnor fiber, what information about the germ can we get out from the Milnor fibers of the chain classes of the Milnor fiber? Going back to Dorf's theorem, Laufer's theorem, how do the chain classes of the smoothing relate, for instance, to the chain classes of a resolution? So those are kind of general questions. Just this. So that's one line of research which I think is interesting and has not been, and many things are related, but these haven't been explored as far as I know. Let me change the topic. Well, no, just a remark. This is more subtle. It has something to do with it. Suppose you have a normal isolated singularity germ, any dimension, and define its holomorphic rank to be the largest dimension of a holomorphic and trivial subbundle of the regular part. how trivial. So this is a complex bundle of dimension n, holomorphic, which is the dimension of the largest trivial subbundle it has. That's a question one can make in general. There's a theorem by Alcides Lins Neto from Brazil that if this is a hypersurface, then the rank is at least one. In all cases, the rank is at least one. That's well known. So for every normal isolated singularity in any dimension, there's at least a one-dimensional trivial subbundle of the tangent bundle. Okay. So he says he proves that the rank is at most 2 for hypersurfaces. And if the surface is quasi-homogeneous, or if n is less or equal to 3, then this is actually 1. Okay. And bad. So one question, what if the germ, this is for hypersurfaces. What about complete intersections? I don't know. And just a remark, the Czariski-Liebman conjecture says that if this fellow is holomorphically trivial, then there is actually no, it's a regular point. Okay? Which is, so these are some interesting questions, I think. Now let me change topic. Consider an isolated complete intersection singularity germ in Cn plus k, and consider a continuous vector field tangent to V and be an isolated singularity at 0. Okay. If it is a curve, we assume it has only one branch. The general case can be, we can deal with the general case, but you have to take into account the intersection numbers of the different branches and so on. Just take a irreducible case. Then one can define its GSV index to be the degree of this map, where this is the Stiffer manifold of orthonormal k plus 1 frames in Cn plus k. You take this, and you can by a homotopy, you can make them an orthonormal frame. Since you are assuming that you have an isolated singularity, all of these are linearly independent because it's a complete intersection, and they are normal to the variety, and this is tangent to the variety. So up to homotopy, this is a unitary k plus 1 frame. So you have this map, and this map have a well-defined degree, because all the homotopy groups of this guy vanish up to before the dimension of this guy, and in this dimension, you have as many homotopy classes as the integers. So you have a well-defined degree. And that's called the GSV index. And then in 98, Tatsuo Suwa and myself proved that if X is a compact complete intersection in a manifold with isolated singularities, and we have a global continuous vector field on X with isolated singularities at the singular points of M, and perhaps at some other smooth points. Then you can define a total GSV index, taking the GSV index at the singularities in M plus the usual Poincare-Hopf index at the singularities of the vector field on the smooth part. You have a global invariant, and then one can show that this invariant does not depend on the choice of the vector field, and it equals the 0 degree Fulton class. Okay? And using this, we prove that the difference in degree 0 of this Fulton class and the Schwarz-McPherson class is given by the sum of the local Milnor numbers. So, what if the germ is not a complete intersection? In that case, the GSV index is not defined, because to define it, we use this frame. There are other equivalent definitions, but all of them use that you have a Milnor fiber. You use that you're in a complete intersection case. So this kind of topological definition doesn't work. Now you can go around it. One way to do it is like with the virtual index that Tatsuo, Suwa, Lehmann, and Suarez defined, and we studied Jean-Paul using the virtual index. But another way is what is called homological index. So so forget for a moment about this index I defined, and take isolated singularity of any dimension and a holomorphic. Now, assume the vector field is holomorphic. Now, consider for each j, the j differential forms, germs of forms on V. Even in such form, you can take the contraction by the vector field, and it gives you a complex. Since the vector field and V have isolated singularity, one has that the homology groups of this complex are finite dimensional. And you can take the only characteristic of this complex. That's a number, a finite number, well-defined number. That's by definition the homological index. Okay, here's the homological index. Theorem: if the germ is an isolated complete intersection germ, this index coincides with the Gibbs index. Okay. Perhaps before, let me make a remark. If we take V to be smooth, this is the usual Kosul complex. And then we know that all the homology groups vanish up to the top dimension, where its dimension is exactly the Poincaré-Hopf index. Okay. So here we have this, and then for complete intersections, it coincides. But the homological index is well defined in general. You don't need to have complete intersection. So here's a question, a proposition. Take an arbitrary compact complex analytic variety, which singularities are complete intersections. No, sorry. Isolated singularities. Now take a global continuous vector field on X, which in a neighborhood of each singularity of X is holomorphic. So you have the homological index defined at each singularity of X. And you have a global homological index, where at the smooth point you take the Poincaré-Hopf. But it's an exercise to show that this number does not depend on the choice of the vector field. So it's an invariant of compact complex analytic varieties. What is this invariant? I don't know. Next topic. This will be very, very short. Now recall that for a complete intersection, the total Milnor class can be defined in this way. It's the difference of the total Fulton or Fulton-Johnson, which for complete intersections coincide, with the Short-McPherson class. Okay. So a general problem, well, Paulo was, I'm not mistaken, the first one in looking at this difference, which then arose in different settings by various people. And the general problem can be phrased as saying, what do Milnor classes say about the geometry of the variety in question? As George mentioned this morning, a lot is known, a lot is to be known. One specific question: are there some geometric implications of the vanishing of the Milnor classes? So, for example, if you have only isolated singularities, the Milnor classes vanish if and only if there are actually no singularities. That's well known. In general, does the vanishing of the Milnor classes has some geometric implication? I don't know.
Do we know how to calculate this?
A lot is known. For complete intersections, a lot is known.
But if it's in homology, then
Yeah, it's in homology.
a lot can be chosen because of the homology group is trivial.
Also in sugar calculus, almost nothing is a complex intersection.
Well, even for hypersurfaces. Work by Paolo and also by myself with all colleagues show that there's a,
But for example, if you assume that your space is projective, you can, by slicing down, move any degree to degree 0. So the projective case, I would guess, in some degree it will be 0 if and only the slicing is. So you can reduce to the isolated singularity case by slicing down this hyperplane, the generic hyperplanes.
Okay. So that would be proving that the Milnor classes vanish if only.
If and only if this generic slice would be smooth.
So how do you say that the Bolton's cluster is slicing?
I mean, by slicing, can you use to a point of characteristic?
Yeah. Let's see. Is slicing for the folding class 2, I think. Yeah. And it's the same slicing as for the Schwarzman-Person class, so you get this correction factor.
Hypersurfaces.
And so there's a correction factor coming in, but since everything is concentrated on isolated points, this correction factor acts as 1, I think, after slicing. So I think in this way, in the projective case, you can move higher degrees to degree 0, which you claimed is understood by the Milnor formula. So my feeling is, in the projective case, if you go to some degree, it would be 0 if and only the generic slicing to that degree which moves this to 0 would be smooth.
So do we know this for an intersection of hyperplanes? So what's the Bolton cluster?
No, for hypersurfaces, the Fulton class just says the class of hypersurfaces.
And then you apply that on the resulting formula because you know that.
Yeah.
If you go back, the degree 0 part of the Milnor class is Paruzinski's generalization of the Milnor number, right? Which is a difference of our characteristics. I'm talking about hypersurfaces. They can use possibilities right under the hypersurfaces.
The question is, of course, here you don't assume that the space has isolated singularities.
That the spaces.
The space. So let's see. So you need, of course, that after slicing you reduce to isolated if you really want to conclude it. No, I make. So I think I make a mistake.
I think that what Peter wants is an interpretation from the other.
Yes.
No. So I think my argument only works for the top degree part.
If you want to draw some conclusion from the vanishing, but I think that
So
some interpretation for the other degrees probably can be interpreted by.
No, for the top Milnor class, there's a geometric interpretation, which maybe.
it's more or less the same. It's what was the Milnor.
Suppose in the simplest case that the singular set has dimension d, and so the top Milnor class is in dimension d, and suppose, this is not general, but suppose that you have a witness stratification, so this guy is a Whitney strata. Under that restriction, then the top dimensional Milnor class is just taking the transversal Milnor number times the cycle represented by the surface. In the general case, it's not like that, but it's something like that.
No,
You take
that's
a-
the same. This is locally the argument. I was thinking globally, but the problem is it only works for the top dimensional piece because by slicing down, then you can get to zero dimensional singularities. Where your Milnor numbers, your only obstruction coming in. Of course, as soon as you have go to lower degree and even slice down in degree 0, but the singularity locus is high dimensional, not isolated. I think we have no control for it.
I mean, the information of the degrees of the Schwarzman-Person classes is essentially the same as the information of our characteristics. Of
Yes, but we
slides.
can't conclude smoothness, I think. You get information.
We have comparisons of some kind of interpretation of it. Readable in terms, but we look at the other ideas.
But in any case, so let's say even this case of top dimension, this is of course a kind of general phenomenon that you say you have two characteristic classes which are concentrated, the difference is concentrated on the singularities, and you would like to understand what is the multiplicity in this top dimensional fundament. Then it's top dimensional is a multiplicity times fundamental class of the reducible component. So you want to put the finger on this multiplicity. And one strategy is, of course, by slicing down. If slicing works for the invariant you're interested in. And this, of course, not just works for these kind of Milnor classes. So that works for Hirschsprung Milnor classes. This is something what Irma and Xavier and Saito are just doing for L-class story to compare with IT classes. It's the same principle. And so if you have a kind of slicing available, you are reducing down by slicing down to an isolated singular situation. And there you hope you understand the situation better, like with your Milnor function.
For hypersurfaces in the top dimensional class is controlled by the top dimensional class in the single class. That is some interpretation.
So for hypersurfaces,
For hypersurfaces,
is it well understood in the behavior of the Milnor classes when you take generic slices?
yeah.
No, I don't understand it, but
No.
Maybe let me also say for projective hypersurfaces, vanishing of Milnor Hirschsprung classes gives you a lower bound on the minimal exponent of the hypersurface. So I think this is a geometric implication.
Yeah, but be careful, then you go to Hirschsprung.
Yeah,
You see more. But as I said, this kind of question one should not just study for Churn. This is a Churn class story, but you can also put in the other characteristics of pictures. And one should ask the same question.
Of course.
But then you can say for all degrees or for the top degree.
If you start vanishing from the bottom, the level you're vanishing, let's say you're vanishing at level k, then the minimal exponent will be greater equal k plus 1.
Okay, so there, of course, there odd information is coming in.
These are these higher singularities. Probably.
So that seems to be a popular thing. He comes
Yeah,
to
just came from a
class.
conference about that.
And
What?
the difference can be in a local cohomology of the singular locus. Or is it
It's automatically. So these kind of questions, they come automatically from they are supported on the single locus because that is the advantage, let's say, working with chow groups or Moore homology, you have a non-exact sequence, you can restrict to the smooth part. But on the smooth part, both classes satisfy the same normalization, so the difference vanish. So that means it has to come from a class of the
Yeah,
single
but
locus.
I
The
mean,
question is a geometric direct player giving you the difference.
So that's something very interesting of the classes that George mentioned this morning. This is a particular case. When you take the difference of two characteristic classes that coincide with the usual chain classes on the smoothing case, then you have variants that are defined globally, but they have support in the singular locus.
But the
That's
question is,
very
of course,
interesting.
so in
Very
this way you
interesting.
only can know it comes from the single locus. The question is, of course, is there a canonical choice? Which here, for example, is possible. And this is the next question. And then the question is, what does it measure?
Yeah, if you have D module supported by some set, its characteristic class lies in support.
Yes, but I think, yes, I think it's, for all degrees it's difficult, so I think the only which I see which is approachable quickly by slicing down is the top component. The others, maybe.
Since you said this slicing criteria, the slicing strategy works first of all for the top dimensional structure. Then when you want to approach a lower dimensional one, then in the normal slice for the lower dimensional one, the intersection with wood has already been there and it's not isolated.
Yes.
So I guess that at that point you need to go to the machinery from the Xerisma in the one sequences and contributions from transversal
You have still results, but the problem is how you want to represent this Milnor class. And the thing is, if these are non-isolated singularities, or let's say for hypersurfaces, we know a lot about of Milnor classes, but for computer section, this is already horribly complicated. So for hypersurfaces, I'm optimistic. We have machinery running.
Yeah.
But for computer section, this is very.
I think if we can understand this even for hypersurfaces, that would be very, very interesting.
For hypersurfaces, one can actually look at the difference of two characteristic constructible functions, right? It's, what is it, nearby cycle function and function one, right in some Grothendieck group. in some
No,
in some
that's of course what I mean by specialization.
Yeah.
If you are in the hypersurface case, with a global function, this is really vanishing cycles coming in. And if you say we have not a global hypersurface, that is where I said we are near specialization. It's coming in. And I introduced a kind of notion of generalized vanishing cycle. So you can represent for hypersurfaces, you can represent this as a German master McPherson class of a God-given constructible function, which measures directly the singularities. And this is just a shadow in homology what you do already for a constructible function. But this is very specific to hypersurfaces.
For what reason is it bound to hypersurfaces?
Because let's say you have a global function, yeah, on a manifold. And the Fulton class you can get as a specialization of the Chern class of the tangent model, of the ambient space. This is the Chern class of the constant function 1. It's a theorem of Verdier that specializing in one parameter families, the constructible function, which is a nearby cycle, translates under the Chern class to the specialization of the Chern classes. Because the ambient space is smooth, that gives you the Fulton class for the function 1. You specialize the function 1 on the ambient space, and that gives you the Fulton class. And that is nearby cycles of the function 1. And the McPherson class of the hypersurface is, of course, the function 1 on the hypersurface. So we want to measure this difference, and this is vanishing cycles of the function 1. The thing is, for hypersurfaces, you can express canonically the Fulton class as Chern class of a nitrile constructible function. And this is specific to hypersurfaces. And that is why vanishing cycles come.
Splicing procedures. My feeling is that they're not very good if you have extra structure on X. Like, for example, having some group action.
That's for sure. Well, it's also I would guess it's not natural to let's say maybe it's not natural to choose the projective embedding. If you have more structure, or you want to stick in a class of spaces like toric or something. Yeah, but this slicing technique we are using in this recent paper I have with Banagel and Dominic, where we prove that IT1 is L for Schubert varieties in Grassmannians. It always uses a kind of slicing technique. But of course, this is very limited. And, the problem, for example, is it does not fit with group actions. It only works for nice ambient spaces where you have enough slices available. So projective space is nice because you have generic hyperplanes. But if you say you go to flag varieties, what are natural slices? It's one strategy. But this is a natural question for whenever you have two characteristic classes.
Absolutely.
And slicing technique would be nice working for the top dimension piece, for example. And we have several examples of this. Yeah, and what is all that in between goes already to the old question, what are these classes in between already? So slices is one interpretation with Paulus, what you call it? Chern polynomial or
So the next question is two example of what if we are beyond the class of local complete intersections. So for example, take the case when you have a variety with a single isolated singularity. What is the difference between the Fulton or Fulton-Johnson and the Schroeder-Macpherson classes? So if this were a complete intersection, this would be the Milnor number. These two would coincide, and the difference would be the Milnor number. When there is not a Milnor number, these two may not coincide, or do not coincide in general, What is the difference? I think absolutely nothing is done. Okay, now let me change topic.
So, but Paulo, what was your proof in the end? You proved a kind of Milnor class. No, you have for general varieties. You have a comparison of these kind of differences on a not on the space itself, but on a boundary buffer. What was it all? You proved a Milnor type formula in general for embeddable spaces or something.
Ah,
You can use the specialization engine.
No.
it's been a while, but yes. I mean, there is a version.
You had a version in the end.
Yes, the version in the end was relying on the hypersurface case after reconstruction that
Yeah.
uses that.
But the thing is, you get some measurement of these differences.
Yeah.
But the problem is they are not measured on the original singular space. You have a space above. So that is the price you have to pay.
Up to yes, but up to push forwards. No.
I do it for the normal bodies. Regular embedding, you can define everything for this.
We are not in the case of regular embedding. This is
Not
any.
Yeah, exactly. Yes.
For regular embedding,
It's understood.
this is completely the section
Yeah.
store. And that you can do with variety specialization. That is what I've done. But Paolo has a result in the end going to any subspace.
It's embarrassing that I don't remember the. I was actually relying on your construction of reduction to the hypersurface spaces. Between the two of us, we should be able to remember what that was.
Yeah, I think there was a trick. You can reduce to a kind of hypersurface situation, which is well understood, but the price you have to pay, it's in the end, the answer is not on the original space.
No, I think the price that you have to pay is that it's incomputable.
That's the problem.
It doesn't-
You
it
want to have
doesn't,
an explicit. You want to have a nice explicit interpretation.
I want to
But the problem is, of course, as soon as you leave this world, even if you stay to the world of isolated singularities, and you leave this world of complete dissection,
and these classes are defined in full generality. These are defined in full generality, and we would have to understand them, the difference in full generality, at least for the case of isolated singularities.
the thing is, you have a Milnor version, and you speak of a Milnor fiber,
But then
but the expected formula will not be true, I think.
But this specialization, to some extent, like there is a characteristic function, a constructible function. Singularities that
There will be a constructive function, so the
measures the difference between the sign of the thing and the restriction of. I guess it's not the tangent bundle to the tangent, but it's the CSI of the complement of sounds like such facts.
What Milnor fiber do you have in this case?
No, you don't have any.
no, you don't have it. That's a problem. No, that's a
Oh, I
problem.
understood you said you have Milnor.
Oh, sorry, no. So the problem is, of course, you cannot speak of so in the complete dissection case, the answer comes from the Milnor. So as soon as you leave this, you don't have the Milnor population available. And the deformation to the normal cone gives you, nevertheless, different Milnor fiber on the deformation space. But what did I prove so long ago?
Nice if we remember.
Okay.
I have to
So
remember.
we can continue with it. But now let me change topic. And we'll come to something that we came in also this morning, spin structures. I didn't write. Let me first say a few words, I don't have it in the slide, about this Rocklin's signature theorem. It's an old, by now almost forgotten theorem. Suppose you have a four-dimensional real compact closed manifold. Okay, and define two-dimensional submanifold. this characteristic if it represents a homology class such that reduced modulo 2 is the second Stiefel-Whitney class of M. Okay, that's a definition, classical definition. So, for example, if M is a complex surface, and you take a representative of the smooth representative differential of the canonical class, a smooth submanifold representing C1, automatically that gives you a characteristic submanifold. But there can be many others. Okay. Then the theorem says that the signature of M minus W squared is congruent to 8 times a certain number, which is this is an element. This is always 0 or 1. Okay. This is associated to a quadratic form on the homology of the characteristics of manifold. Under these conditions, one can show that this determines automatically what is called a spin C structure on M. And the spin C structure restricted to W actually gives you a spin structure. So in this setting, W automatically comes with a spin structure. Okay? Okay, now suppose these are complex manifolds. A manifold and a submanifold. Then definition on a complex manifold, spin structures correspond to what are called theta characteristics, which are line bundles that square are the canonical bundle. That's a theta characteristic, and those correspond projectively with the spin structures. So now let's come to the complex varieties. This is a work I did long ago with Elaine and Eckhart Giffen. And you have a complex variety, then you can define a theta characteristic to be the isomorphism class of a holomorphic line bundle, which square is the dualizing sheaf. Okay. And then we said you can call that a spin structure. In the smooth case, that's spin structure. In this case, it's just a name. We did nothing with it. Now, suppose you have a compact manifold, the normal definition, and a divisor, a positive divisor. We say that this positive divisor is a characteristic divisor if this is the divisor of this type, where D is on holomorphic line bundle. Why the name? Because if you have such a divisor and you look at its homology class and you reduce it mod 2, it is the same class as the canonical class mod 2. And if this were smooth, I mean, that would be the definition of a characteristic submanifold. Okay? And because this modulo 2 represents the Stiefel-Whitney class, so this is equivalent to saying that this represents a homology class whose reduction modulo 2 is the second Stiefel-Whitney class. Okay. Now this is not a definition, this is a proposition, sorry. If W is characteristic for M, then one can show as an exercise that the bundle L restricted to W, well, that the bundle L is of this form, is the dualizing sheaf, well, this is a manifold, so this is the canonical bundle, the anti-canonical bundle times D square for some bundle D, and restricted, if this is not empty, restricted, this bundle restricted to W is the dualizing sheaf of W. Okay? Sorry?
That would be a tensor.
Yes, sorry. This O plus is tensor. Yes. This O plus should be all times. Sorry. Okay. And I don't know. Then given a characteristic divisor, this is a definition that comes from Atiyah and Rees. Atiyah and Rees prove that whenever you have a complex manifold with a spin structure, you can define its mod 2 index in this way, and this is the mod 2 index of the Dirac operator for the spin structure. Okay. So we take the name and we define a mod 2 index in this way. Is this the sum of these homology groups? I didn't put the dimension. These are characteristic divisor in a manifold of dimension 4k plus 2. Okay. So the ambient manifold has dimension 4k plus 2. Then you take the sum of the dimensions up to below the middle. So for example, if W were a characteristic divisor in a complex surface, you will be taking only H0. You take that number, and then the theorem we proved is that under these conditions, this mod 2 index is just the reduction mode 2 of the analytic Euler characteristic. And then it's an exercise to show that if K is 0, so if you're in the case of compact surfaces, this is just Rochlin's theorem in the classical case. So now the question is precisely if anything can be said, if there anything interesting can be said in the case where X also is a singular variety. All the definitions make sense. You can define whatever you want, provided you prove something interesting. I don't know if you can prove something interesting.
But you lose interpretation of the Dirac operator.
We don't have that. And I don't know if you have some kind of problem of theorem in this sense. No? I don't know. So, in summary, this theorem is giving an interpretation of Rochlin's theorem in the complex analytic setting, because in that case, W had to be smooth. Here, it can be a divisor, but M has to be smooth. So, can this be done more general? I don't know.
Okay, the problem is, of course, as I mentioned in the morning, so you don't have any good definition of the singular spin space.
A good definition of what?
Singular spin space with a spin structure. So
No, the definition we are giving is arbitrary, is this one. We are saying that the spin structure means square root of the dualizing sheaf. That's somehow a natural extension of the concept.
you don't have a dualizing sheaf on any analytic space. You need a restriction.
The dualizing sheaf is sorry?
There is already a bundle, so as but will be a bundle, and omega is a bundle.
So first you want to have a dualizing sheaf.
Yeah, that you
Then
have.
you need Gorenstein.
No.
No? You have a dualizing complex, but not a dualizing sheaf. So what do you mean by a dualizing sheaf?
No, the one that gives you the
It's
set
a
duality.
top-dimensional piece of it, or what?
No, you have set duality.
On a singular?
Yes.
No, you need a dualizing complex. This is not coming from a sheaf.
That's still the count.
This is Rotendiek duality. You have not. You need that the analytic space is Gorenstein, so that the dualizing
You're
complex
right.
is
You're
taken
right.
to
You're right.
one
You're right.
degree.
You're right.
But this still is a coherent sheaf. This is still not a line bond. In your situation, you would like to have it a line bond.
Mm.
So that means you have to say this is an analytic space which special
Yes,
type.
yes, 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 yes.
What if it's pure Gorenstein? That means that not the square, but some higher power is the power of omega.
Could be.
But in any case, maybe even you assume that you have, it's Gorenstein and the dualizing sheaf is really line one. Could be the case. So
Yeah.
it would make sense.
Then what?
Then what?
Yeah.
So,
Yeah.
so is this a definition of a singular spin space for you? Or that's
That's why I said you can define whatever you want, provided this is of any use.
that's the question.
I
You
don't
can
know if
say
this is of any
this
use.
would be a definition of maybe of a spin structure on a suitable singular space, but you don't have the direct operator available. And so what to do with this? This is difficult.
For us, this was very useful because we used it on the characteristics actually here. This is singular, and this works in this setting. In this theorem we proved. And we also use that for the case when this definition makes sense also for non-compact varieties, assuming the divisor has compact support, and we use it for the case of a resolution of a Gorenstein singularity, and then gives you something related with the geometric genus and so on.
Yeah, so this is of course related to Gorenstein singularities.
Yeah.
And then it's maybe
Okay, so this definition makes good sense for us
it's a suitable notation.
for the case W singular, but very special setting.
Yeah, but
In general, I don't know.
no, but then of course coming to this result of you, maybe this is the right kind of definition here. But I would speculate, if I remember correctly, if you look at elliptic classes and rigidity of characteristic classes. So elliptic genus was, the real elliptic genus was coming in because this is rigid for spin manifolds. It's a fiber. The fiber is a spin manifold. I think that was the original. And I think
But
for Taro,
also you need the transition group.
in good situations, he was coming from that the fibers are spin manifolds, and I think for Taro's extension to the complex world, the analog in a different way. What would be maybe a definition of a spin manifold, or what should be the counterpart of spin manifolds, where holomorphic manifolds with first vanishing Chern class. This is another kind of analog of not what you are taking. So he was proposing from the viewpoint of rigidity, these are SU manifolds. For the complex elliptic genus, then you have rigidity with these fibers and connected structure groups, and so on. So there are many views on the market to you can say take this as a definition of a spin manifold.
Yeah.
Has nothing to do with your theorem anymore.
Yeah.
And maybe this has also the chance to extend to singular spaces. You can say you can give sense to the first Chern class and ask this to vanish. But you see, as soon as you go to singular spaces, there are choices. Even if you can do it, it depends what you want to do, what is the choice you take, and spin manifolds is something we miss. But in any case, this is an example to remind me that you have an answer in this special case.
Okay, so I think that's it. Yeah, that's it.